Okay, welcome back to numerical analysis. So, as much as I like my little MATLAB at midnight segment, yeah, I think it's really hard to motivate myself sometimes when it gets late at night to actually code and sit down or do a full recording. So I fell behind a little bit on some of these computational videos. So today I'm just going to run through and talk about numerical integration, and in this case I'm going to do the trapezoid rule. The trapezoid rule is pretty simple. Basically you take a whole bunch of points, and then we're doing sort of a whole bunch of samples of your function uniformly spaced for what we care about, and what you do is you just do a numerical routine where you basically do a linear interpolation between each individual points, and then you basically compute the integral, the area of a trapezoid. And so you add all those up and it should give you a good approximation, and yeah. It's also very, very simple to code up in MATLAB itself, and so I'll show you how to do just the trapezoid rule, and then I'll show you how to actually compute an antiderivative using a matrix that we can make out of trapezoid rule. This matrix has an added advantage of giving you a discrete version of integration and also then a discrete version of differentiation. And later on we'll see how good that does as being a numerical derivative when we talk about differentiation next. In any case, so we can talk about Simpson's rule later. It does do a better job, and once we have the trapezoid rule we can do sort of a comparison between them. But for the meantime, yeah, that's what we get. Alright, so I'm going to stop here, and we're going to jump into MATLAB on my computer. Alright. Okay, so what we're going to do now is we're going to go through the code, and I'm going to show you how to set up trapezoid rule on this function here. What I have set up here is a function. We already have the function f. Here it's just a circle, and we might change it later. And so to real quick show you what's going on, I just set up something we've already done before, and so I set up a plot command. So I have two different t values I want to go through. I want to go through the sample points, which I'm right now is spacing every quarter unit between -1 and 1. And here this is all my plot samples, and so it's 0.01, so I made it a lot more fine. And so so this first bit is just going to plot the function, and the second bit will plot my samples. This one, because I put RO, it's basically going to give me red circles instead of connecting lines. And here I just put G. It basically means it's going to give me green lines. So so then you get to see what we're doing. So in blue here, what we have is we have the circle itself. So this is the thing that we're trying to take the integral of, and or at least compute the area under the curve. And the green is basically the linear interpolation that we're doing with the trapezoid rule. And so and then beyond that we have each of these sample points are the equally spaced points that we're going to be computing. So we have, starting here at -1, we go up every 0.5. So here this should be at what? Yeah, -0.5. And so this goes another 0.25, not 0.5 each time, sorry. And then at 0, 0.25, 0.5, 0.75, and then up at 1. Okay, and so this is going to be our first round of doing our numerical integration. Now, if you remember, basically with the trapezoid rule, we're going to take 2 points and we're going to add them together, and we're going to add them together and take their average and then divide by the step size. The step size here is going to be 0.25, and so let's go ahead and start taking a look at that. So so basically I'm going to say 4i goes from 1 to the length of the samples. And we're going to go up to 1 less than that, because you need 2 points for every sample. That means that you're going to be either shaving the front off or the end off, right? now I'm gonna just say call something the integral sum, say trapezoid rule. I'm gonna set equals 0. So what I'm gonna do each time is I'm gonna throw the integral inside of this, and so it starts off at 0 because we haven't added anything to it yet. But then each time I go through a point, I'm gonna go ahead and add it into into this quantity. So how do I do that? So I basically say I'm gonna take the this value, the integral trap, and then I'm gonna add my samples, and then bit at a time. So it's gonna be f of t samples. We're gonna start at 1, and I'm gonna add f at t samples at 2. But it shouldn't just be 1, right? We start at 1 with our index, and so it's gonna be I. Instead of 2, I'm gonna put I plus 1, right? And so there we go. Now I need to take this quantity and divide it by 2, just like what we computed in there. Basically, yeah, that's what it is. And then we're going to multiply times our step size. And so here is going to be 0.25 here. There we go. Okay, so I'm going to stop here, and so for this area, we know that the area that we're trying to compute is going to be the area of the unit circle divided by 2. And so we know the area of the unit circle is going to be, well, its area of a circle is pi r squared, and so it's going to be pi times 1 squared, just pi. And so what we should see is pi over 2. And so it's pi over 2, 1.5708, right? So let's see how close we get. And so at the end here, I'm just going to tell it to tell us, I'm going to say display integral trap. So it'll tell us what that value is. All right. And so boop. So here, that's what it gives us. And that does not seem very accurate. It's really, really not accurate, actually. So what did we do wrong? Well, if I look back over here, I just keep setting integral trap equal to this, and that's not going to do us any good. We need to increase it every single time. So what I'm going to do is I'm going to take integral trap, and I'm going to add to it. And so now that actually will increment for each new development. So let's go ahead and do a try again. There we go. That's much more what I expected. It's not perfect. It's 1.4979, but that's definitely a lot closer than this. This was just one little piece. And so at the end here, we wanted 1.708. All right, so we want to be able to increase the accuracy, right? And so how do we do that? Well, I'm going to make a new quantity. I'm just going to call it h. And so this is going to be our step size. And so right now is 0.25. And I'm just going to go ahead and replace these guys with h. So that becomes h, and that becomes h, right? And so let's go ahead and press play. Boom. All right, same quantity. I just wanted to check to make sure it was giving me the same exact answers as what I was getting before I start manipulating things. It's a good programming practice. All right, so now let's change it to 0.1. Let's see how much closer we get. All right, so this is a lot closer. So again, we're looking at this quantity. That's our goal, is 1.5708, and we just got 1.5523. So we're off by 0.02, and that's an improvement. And so we see we're using a lot more points here, though. Good. Let's see if we can do even better. Let's go let's say 0.05. This is actually only it's getting close to what our actual sample size are. Sample size is here. All right, so this is 1.56 as opposed to 1.57. So that's actually pretty close, though, honestly. I mean, if you even look at this, I mean, you can't really see that much of a difference. What's killing us here, though, is this jump here. It's pretty dramatic. And so it turns out that the integral here that the function that we're trying to integrate isn't actually differentiable on either endpoint. It's differentiable on the inside, so we actually will get if we restrict ourselves to integrating only this region, we'd get pretty close pretty quick. But the reason why we're having trouble, even with so many sample sizes, of getting this sort of integral here, it's just because it's an unbounded derivative, and so all of our differentiation remainder formulas rely on us. All of our integration formulas all rely on us having higher order derivatives in order to improve that. And so with the trapezoid rule, in order to use our convergence rate that we established, we need it to be 3 times differentiable, but this isn't even 1 times differentiable on that boundaries. On the inside, it's infinitely differentiable, and it's not a problem. But just on those endpoints, -1 and 1, it can be problematic. So, just for the heck of it, let's do 0.01 and see how accurate we get. Boom, 1.702 versus 1.708. Yeah, so we got 3 digits of accuracy, and that's pretty good. And we see we have a ridiculous number of sample points. Let's see, just because this is all happening pretty fast, let's see what we get there. All right, so this time we got 1.5708, and that is with a heck of a lot of samples. It's actually more than what we were sampling before with this. And so if I do length of t samples, how many do we have? 2001. So that is quite a lot. All right, but with 0.1 accuracy, we still get pretty good estimate. It's just killing off those last few digits. It takes a little bit more time. Okay, so that's great. That's the loop version of this. How do we turn this into a matrix thing? Because MATLAB is the matrix laboratory, and so if we cleverly construct a matrix, we can actually go ahead and set up a whole anti-differentiation routine. And so what I'm going to do is I'm going to go ahead, I'm going to save a new file, save as, and I'll say trapezoid rule antiderivative. Okay, so we should talk about this a little bit. So in here, we see that we're going from sample ti to ti plus 1 and dividing by 2, and so that basically means everything about the first and the last sample are actually used twice. And so basically what I can do is I can write this as say h over 2 times 1, 2 to 1, and if I multiply that by the samples, say, so we have a row and we multiply it times a column, it's going to actually turn that into just a quick integral. So you can say, say f of t sample 1, f, so this needs to be a column vector, f of t sample 2, and let's keep it up, f of t samples 3, and f of t samples 4. This would do basically what we want. That should be samples here and here. And so it's not too illuminating because these aren't the right samples, but if we go ahead and change this to being 0.5, boop. So basically these guys, I want 4 samples. So let's say, say 2 divided by 3 is, I think, it'll end up working for us. So yeah, 4 samples there, and so that gives a 1.2571. And now let's take a look at what happens if I do this. Gives me exactly the same answer. So so this is a matrix formula of what we're doing. So basically we take h over 2 and we factored it out. And when we did that, we're left with 1, 2, 2, 1, and then multiplied by our samples. And so this is a row vector times our samples. So what I'm going to do now is I'm going to make a column vector of all of our samples, and I'm going to make a whole big matrix that is a triangular matrix that starts at 1, and then goes 1, 2, 1, and then 1, 2, 2, 1, 1, 2, 2, 2, 1, etc. And then after I multiply them, each row out of the resulting matrix ends up being the integral over an increasingly wider band of our function, and which gives us an antiderivative. So, so then let's go ahead and figure out how big that matrix needs to be. Okay, so let's say we have basically, if we want for 4 samples, if I want to do this sort of thing, then our matrix needs to look like this. It needs to be 1, 0, 0, 0. And then the next row needs to be 1, comma 1, 0, 0. And then the next one is 1, comma 2, comma 1, comma 0. And then the next one is 1, comma 2, comma 2, comma 1. Right, that's the sort of matrix I'm looking for. Now that top entry is not actually going to correspond to the trapezoid rule, but it makes the matrix ultimately invertible, which would be handy for us. And ultimately, it'll give us sort of a left-hand rule for the very beginning part. It'll just give us h over 2 times that point. So it'll be like a very small increment of h over 2 for that first bit. That's fine. So I want to make this matrix a lot more general. So for 4 points, we end up with a 4x4 matrix. And so we're going to take the number of samples that we have, and we're going to make that matrix for it. So we have t samples. So what I want is I basically want a matrix M that I'm going to say is 1s times t sample, length of t samples. Right. And so boom, right? So that's a good start. It's not exactly what I wanted though. So I'm going to say M, I also want this to be twice of M. Okay, good. So then what I'm going to want is I'm going to make that 1, 1, 1 here, 1 here. All of these become 1s, and everything in the top bit becomes 0. And so what I'm going to do then, I was going to say a trill of M. This gives me only the lower triangular portion of M. So now we have all those zeros. Now I'm going to turn all those guys on the left-hand side of M into 1s. That's not too bad. There's a bunch of ways you can do this. You can go and set up a loop and just take a look at those. But here's a slick way to do it. So that selects all the rows on this one column. And I'm going to replace this with 1s that are, say, length of t samples, and I want this just to be that many rows with one column. Right, so boom, there we go. So that just changed these guys here. Now I just need to change the diagonal. It's hard to do this in a slick way, so I'm just going to go for I is equal to 1 to length of t samples, and so I just make sure I cover each one of the diagonal elements. And so I'm going to say MII is equal to 1, and boom, I was M. Ta-da! There we go. Okay, so that's how we make M. So we now have a matrix to do that. And since if you go and press up and just hold shift, you can copy all of these guys. And now I've copied all the commands, and now I'm going to pop it up in here. Boom. Okay. So now, what are we going to do? So now instead of putting the integral one at a time into this and here, we're not going to do that. And so this gives me my trapezoid matrix, M. And so I'm going to copy this over, put it out here, do some nice tabbing here, and there we go. And put semicolons next to all these guys. We don't need to report every single time we do this. Okay, now what am I going to do? I'm going to take, we need to have our sample vector. And so our sample vector is just going to be f applied to t samples, and we're going to make it into a column vector because these guys always give you row vectors. If I take t samples and I take a look at it, for instance, here, delete all that. It's just a row vector. I want to turn it into a column vector, so I put the apostrophe there to transpose it. Okay, and so I'm going to call this sample vector. Right, and now to execute the antiderivative, I'm just going to basically take my antiderivative from samples is basically going to be m times my sample vector, and we need to multiply by h over 2. And there we go. And so, what do we get? Let's see. So I can go ahead and kill this, and let's see. I'm just going to push play, and I'm going to show you something. So pushing play, boom, gives us our samples. And what did it give me as far as my the last entry here? Whatever that should be the antiderivative we got when the integral that we got after all of this. And so let's take a look at the last entry here. So we have this guy, and I'm going to put in end. What do we get? 1.2571, and is that indeed what we had before? It's 1.2571. Okay, so the integral is actually working. Okay, so now, but what's cooler is I can go ahead and plot this. So so then we can go ahead and plot figure plot t samples comma oh, I already copied that, antiderivative from samples. All right, let's see what we get. All right, so we have two different things. So we only had 4 samples, so it isn't that impressive. But this is the antiderivative of this guy. Okay, now let's increase the samples and see what we get. All right, so I'm going to increase the samples to 0.1, and should get something a little bit smoother. Okay, so here we see we're getting it sort of flat entries here, and we know that this function here has zeros here. So the antiderivative should be flat in those areas. That should be local extrema. Okay, now let's take even more. 0.001. Alright, just go nuts. Alright, so there we go. We use a lot of these points, and then we computed antiderivative. And yeah, so that's pretty cool. But let's do something that we're maybe a little bit more familiar with, and let's just change this to a line. And so we know a line should turn into a parabola when we integrate it. And so let's see what we get. Boom. So we took a line, and we took all those samples, and we did numerical integration. And all along here, this is what we get. We ended up getting the parabola. The parabola should correspond to x squared over 2-ish. Yeah, it should be x squared over 2. But it ends up being shifted down just because we started with all these, because we integrated negative first. But yeah, there we go. Okay, cool. So that gives you the trapezoid rule antiderivative. Now, something else you can do is you can take antiderivatives with it, which is pretty neat. And so I'm going to save yet another file. I'm going to say trapezoid rule and differentiation. What the trapezoid rule does is it gives us a numerical routine for doing integration. And now we get to see how it does as far as numerical differentiation, because we know that integration and differentiation are inverses of each other to an extent, up to boundary conditions and fixing one point. And so we hope that we can get numerical differentiation. I haven't even tried this yet, so we'll see if it does anything credible. But yeah, but basically what I'm going to do is I'm going to take my x squared function over 2, and we should see a line. when we anti-differentiate. But if we're anti-differentiating, what we need to do is we need an inverse. We need to take the inverse of this matrix, and that is the inv command. And so what do we get? We take our samples and this, and let's see what we get. So it gives us a flat 0. All right, so that wasn't encouraging. Well, maybe not. Let's see. For some reason, it's giving us really, really big boundary here. I see. So, was a moral here. So, boom. Trying to do this as strategically as possible. So it gave us something. It gave us some sort of numerical differentiation routine. We see that it is linear in a sense, but we have this problem where basically it's just this huge band and it's hard to make out anything out of it. It's not a very good numerical differentiation routine, and it looks like it's very, very sensitive to, well, pretty much anything. We could try to do some ways of filtering this, but that's why we have actual numerical differentiation routines to play around with. And so, yeah, so don't do this at home, kids. All right, okay, so I think that's where I'll stop here, and I hope you learned something. And yeah, there was more I wanted to say, actually, but yeah, probably should stop here. Okay, all right, bye.